So in this video, we're going to talk about how you would actually find an empirical formula based off measurements you took in the lab. And through this video, I'm going to give you some kind of off and on discussions about possible alternatives, possible routes. But the big thing here is that you went to the lab, you had a sample, and you wanted to figure out its empirical formula based off what you found in the lab. Now, full disclosure, this is a bit of a hard video to do off of my shoulders, so I'm going to have to be working with the sheet here. It's going to be a couple minutes where I really need to kind of just look at the sheet, so I apologize for the audio dropout, but it is what it is. But let's say you go to the lab and you analyze a sample, and you find this sample contains vanadium, phosphorus, and oxygen. There's a lot of different techniques that can get you this information. But you say, okay, I've got a sample that was 100.125 grams, and through various analytical techniques, I found that it's 44.614 grams of vanadium in there and 18.114 grams of phosphorus in there. What's the actual empirical formula? So the first thing we're missing here is this component oxygen. So the easiest thing to do if we cannot directly measure it is to sit back and say, well, this mass represents vanadium, phosphorus, and oxygen. We're just going to take the 100.125 grams and subtract off our mass of vanadium and our mass of phosphorus. And this will give us a mass of oxygen, going to the cheat sheet here, of 37.397 grams. So this is the easiest way to find the missing component, but it's also the least reliable way of doing it. Because these are very hard numbers to measure. Any type of mass that the compound contains, there's going to be error bars on it. And those error bars are going to start adding together as you start subtracting them off the total mass. So we got a plus or minus on this number and a plus or minus on this number. We're going to combine those error bars to get this one. So the more things we have to subtract off the total mass, the less and less reliable our numbers become. And so in the case of our empirical formula here, our oxygen is going to be the least reliable measurement we take because we had to find it by subtracting off the other masses, which also had uncertainties associated with it. Now, an alternative to this, if you could do it, you would directly measure the mass of oxygen. Here's the problem. If you directly measure the mass of oxygen, again, you've got error bars. And if you add the three masses together, you don't necessarily get the total mass. That's fine. In situations like that, you're just going to rely on the masses by themselves and then use those to do the next steps. But again, it depends on how you're able to take your measurement and what you end up having to do in the end. That'll dictate how you get all these numbers. You can't proceed to the next part of finding the empirical formula though until you get these numbers. Now, what you can do with these numbers before you even start going to empirical formulas is find the mass fractions. So if I wanted to know the mass fraction of oxygen, just as 37.397 grams divided by the 100.125 and so forth for the other ones. But we're not doing that. We want to find empirical formula. So to find empirical formula, the first thing we have to do is go to moles because your empirical formula is a mole ratio between the different elements within the compound you're looking at. So in the case of vanadium, we're just going to take the mass, divide by 50.9 grams per mole. For phosphorus, we're going to divide by 31.0 grams per mole. And for oxygen, we're going to divide by 16.0 grams per mole. Now, oxygen is a diatomic gas, but we're not talking about a gas here. We're talking about the element oxygen. So we're only divided by the 16. And what this will get us for moles is 0.87653 moles of vanadium. 0.58433 moles of phosphorus. And 2.37313 moles of oxygen. Now, at this intermediate calculation, ideally you don't round. You want to keep all the decimal points in here because this is an intermediate calculation and you don't want to get errors associated with rounding. Now, that said, if you were asked to report moles, you want to do the correct sig figs, but any following calculations would carry these numbers through. But these are the moles I get if I convert all these masses to moles. Now I'm ready to take my experimental data and try to derive the empirical formula. And to do that, I'm going to divide it by the smallest number of moles. So I got 0.877, 0.584, and 2.34. So I'm going to divide them all by the moles of phosphorus. So that's 0.584, everything that goes with it, 0.584, everything that goes with it, the 2.367 by the 0.584, by everything that goes with us. And I'll get a number. And these numbers I'm going to get are going to be the subscripts in my empirical formula. Now, I'm going to give you a number. We're going to go back and talk about the numbers we're going to have down here. But if I take 0.877 divided by 0.584, I get 1.5000 dot dot dot. For phosphorus, divided by itself, 000 dot dot dot. And for oxygen, this is going to be 4.1 dot 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 dot. Now, here's where you're going to have differences in textbooks and instructors. A true empirical formula does not have decimal points. And the reason it does not have decimal points is it is an infinitely precise number. We can't write an infinite number of zeros. So when we have something like sodium chloride, NaCl, or probably a better example, calcium chloride, CaCl2, it's not 2.000, it's 2. So some instructors will tell you that you need to get rid of these decimal points and only work with integers, but there's two major issues with this. One, it's kind of a misrepresentation of your number. And so if you have this CaCl2, but you really got CaCl 2.9837654 or whatever, you're not really reflecting how well you knew that number. And the second is that there is an instinct that if you end up with a number like 1.5, you're just going to round that to 2 because you're being asked to find an integer. So yeah, you can see the argument for saying it should be an integer because there's no reason to say that there's 1.5 to 1 to 4. But you can also see the argument saying that, well, you need to keep the decimal points to reflect how well you know the answer. Me personally, I like to keep the decimal points for two reasons. One, you do need to reflect how well you know those numbers. And the second is that it's going to help you catch on to the fact that if you end up with a number where the tens position, not the number itself, but the tens position, the point something, is between 0.3 and 0.7, you either need to multiply by 2 or by 3, the whole empirical formula, in order to get rid of those numbers. The reason is that if you're seeing this 0.3 to 0.7 number, it usually implies that your empirical formula is overly simplified. So if you look at something like, sorry, I'm trying to come up with an example off the top of my head. For whatever reason, we had something that was in a 2 to 3 ratio. Well, that would be 1 to 1.5, but we'd have to double it to get to that 2 to 3 ratio. Same thing's true here. The reason we had this 1.5 is, one, this is a really well-cooked problem to illustrate this point. But the second is that this really is V2 or V3, V208. And the reason why we're getting the 1.5 is we divided this whole true formula by 2, and this gives us the 1.5 and the 4. So if you are going to do the thing where you want it to be only integers in the empirical formula, some instructors do that, and there is actually a good justification for doing that. Before you round, don't round immediately. Look at these three numbers and see, does it sit between 0.3 and 0.7? If it sits around 0.5, double it. If it sits closer to 0.3, triple it. If you do that, and you're still ending up with 0.3 to 0.7 in one of your coefficients, go back to the formula you originally got, multiply by 4, multiply by 5. Do whatever it takes. But what you ultimately want to end up with is something that looks around between 0.2, lower than 0.2, or higher than 0.8, because in that point, it's probably just rounding. It's just scientific error that's creating that not quite a decimal point. At that point, you will round to integers, because you can be confident knowing that you're really truly rounding something close to the number you're looking at, not something that's really far away. So, to summarize, go to lab, sample weighs this much, you find this many elements. If you're missing one of the elements, take the mass of the other element, subtract it off the total mass, that'll give you the mass of the missing component, but it's also going to be the number, the component with the least accuracy in it. Once you've got the masses of all your components, convert them to moles, divide by the smallest number of moles, build your empirical formula. If you're going to round to integers, before you do that, make sure this looks close to a chemical formula. So the decimal points, that tens position in your empirical formula, is less than 0.2 or greater than 0.8. If it's between 0.3 and 0.7, you either need to double or triple the whole empirical formula. Between 0.2, 0.3, and 0.7, 0.8, kind of a gray area. When you finish, I prefer to report all the sig figs to show that's how well I knew the numbers. That said, if you are being told by an instructor or you prefer, you can go to integers. It's only after you do the doubling or tripling, if it needs to be done, that's when you're going to round it out. And that's how you find the empirical formula based on experimental data.